Greetings and welcome to a new video about Extra Element Theorem. We will discuss this to determine the transfer function of a relatively complex RL circuit. We will see step by step, of course, how it works and also verify that in SPICE simulations. Alright, we have the following objective. We would like to use the Extra Element Theorem, EET for short, to determine the transfer function given A in the Laplace domain VO over VI. We have here our circuit, we see here the AC input voltage, and we measure here the voltage across these two nodes. We have 3 resistors and 1 inductor, which is then in this feedback configuration. So how do we work it out using this Extra Element Theorem? We have discussed this in the previous videos, so we will apply again the same step to determine our transfer function. Now, in general, we know that our formula for our transfer function is given by this expression. We have here a couple of elements, couple of parameters. First one, we like to determine our transfer function where the element we call the extra element to be infinite. Then we have also this nulling impedance and the driving point impedance. The Z here is the impedance of our extra element. Everything will be clear shortly when we go step by step in our analysis. In this case, we will designate the inductor L as our extra element. And in this case, as we said, the Z will be then our impedance of that element we have chosen, which is in this case the inductor, and that's given in the Laplace domain S times the L. Alright, so we are actually ready to start. First, we show the calculations and then we will verify that in the simulations. Step 1 is we will remove our inductor from our circuit and then calculate the voltage gain. So that's actually what happens. So you remove it, that is actually this part of the equation or the formula. So we will have the VI again and the 3 resistors, and we will measure again across the same 2 nodes. Well, since this is an open circuit, there will be no feedback connection anymore. And the current through resistor R3 is 0, and that means the voltage across that resistor is also 0 volts. So we have effectively R2 over R1 plus R2, which is the voltage divider, and that will be the ratio in this case, which is defined then as the gain, specifically where the extra element is open or have an infinite value for the impedance. So that's actually this part, step 1. Step 2 is to disable now our input source. In this case, that means shorting our input voltage source, and we will determine what we call the driving point impedance ZD between the inductor nodes we have here. So the circuit actually will be this. So we have our short here, VI, and there's an open circuit here again where we have our extra element, and we will look between these 2 nodes to determine the impedance, what we call the driving point impedance ZD. So how do we do that? Well, we see the R1 and R2 are now effectively in parallel because this node is effectively grounded. And then we see here actually that the R3 will be then in series with that parallel combination of R1 and R2. So our ZD is the parallel combination of R1 and R2 plus the R3. Now R1 and R2 is given by this in the parallel combination, and that will be then worked out the expression for the ZD. Alright, now the step 3 will be then null the output node, that means not grounding but make it the 0 volts, and then determine the nulling impedance Zn between the inductor nodes again. So the circuit will be there like this. So we have our input voltage back, that will be not anymore a short. We have here our output voltage and we null that, that is actually what it means. So this potential here at this node is 0 volts. We have again our open inductor and the rest of the resistors are in place. And where we look at it is now again between these 2 nodes, and that is our nulling impedance. In this case, it will be better to apply here a test source and then determine the Zn. So I will bring up again the same circuit and then apply here what I call a test source, VT, which has in this case a polarity like so, and then the current flow will be then from left to right. Well, we will use the VT and the IT, which are the test voltage and the test current, and the ratio of that using just Ohm's law will be then our nulling impedance we are looking for in step 3. So we'll work it out here, and we'll see that IT here is flowing like so, and we will see how that works out on the rest of the parameters. In this case, we have also the voltage across the resistor R1, and also the voltage, and there also is associated current in this case, of course, going like that, and the voltage across the resistor R2, and the current is going up from plus to minus. And we have here the voltage across the resistor R3, I call it V3, and then the current goes like so. The IT will be again flowing in this way because there is no current path here in this case. So we have here our IT, and now we can develop the equations to determine now the ratio VT over IT. In this case we see the V2, which is our voltage across the resistor R2, is also equal to V3. Why? Because this node is effectively 0, which is also actually connected to this ground. That means in parallel with the resistor R2. And that means if I know the voltage across the R3 or R2, that doesn't matter, I also know actually the others. So if I say R3 times the IT is the voltage across the resistor R3, that's the same voltage across R2. That's actually what you see here. Now the current through the resistor R2 is then taking that voltage we just determined and divided by R2. That's actually what you see here. So we relate actually the current here using the voltage across R3. We also know the current here, I1, is produced by I2 and IT. So these two together make up this I1, which is actually the Kirchhoff's current law at this node here. And that's shown here. And we also know that I2 is from this second equation is R3 over R2 times IT. Now we have here an expression where you see actually the IT and the ratio of two resistors. Now in addition we can say the voltage we have here as the test voltage between these two nodes is actually the voltage across the resistor R3 plus the voltage across R1, which is then V3 plus V1. What is V3 and what is V1? Well, V3 we already have it here, which is R3 times IT. And V1 is actually the Ohm's law again, R1 times this I1. And I1 is actually shown here. So that means we have to multiply this by R1, shown here, and then we have our voltage V1. Now you see here actually an interesting situation, a nice expression actually. VT is now in terms of the resistors and only IT. That's exactly what we want because we like to go for the ratio VT over IT. So what I will do is I will actually bring up everything inside the parentheses and then take out the IT outside. So we have here R1 times this and R1 times that, and also R3 is here alone, and that means complete thing will be then times IT. If I now take the ratio, I have only this part in the parentheses, and that's actually shown here. And this is now our nulling impedance. So I will make it in the box here, and you see actually the expression we are actually looking for. Okay, this part is of course the hardest part because you need to apply the test voltage and the test current and then take the ratio, but the procedure is actually quite straightforward if you apply this several times and also use the handy work from the Kirchhoff's current law and the voltage law and the Ohm's law. Alright, now take this here, we have our two important parameters for our formula, and now we will go for step 4, which is then use a formula for the extra element theorem, which is actually substitute this one. We need the step 1, step 2 and step 3 answers, and that's actually what we see here. So we have here R1 and R2 here, which is the ratio, and we have here 1 plus the Zn over SL, because that was the Z, and over 1 plus Zd over SL. Now what is Zn and Zd? That's shown here. But we can also rewrite this in a form that we have the numerator and denominator actually as SL plus the Zn, because just multiply the numerator and denominator by SL, which is also the same here then with the Zd. This is more convenient and also handy to designate the poles and the zeros later. Okay, I will bring up now again the Zd and Zn here, and then we have the following expression in full detail where you see actually here the Zn and the Zd worked out in full detail. Now if I look at the pole frequency means actually the denominator making to 0, That means the SL plus this part is equal to 0, and then you work it out, you get actually the S is equal to minus this resistor part divided by the inductor value. And the 0 frequency is again the similar form. You take the numerator, you equate that to 0, and you solve for S. And that is actually what you see here. Now this is defined as the pole frequency, and this is then defined as the omega z, which is the 0 frequency. This minus sign is just to show you that it is on the left plane of our complex plane. Next one, we will look at a DC gain. The DC gain can be determined by looking at the circuit. You see that the inductor will be at DC as short. That means actually the input node here goes directly to the output, which means there's a transition of 1. That means the gain is actually 1 over 0 dB. What happens at high frequencies? Well, high frequency meaning that omega goes to infinity, then the impedance of this inductor will be then infinite. That means that we have an open circuit here. You get the exact same result as we have it for this A, for the condition Z is infinite, which is then R2 over R1 plus R2. And that is then in this case, of course, determined by the resistors. Now we have our selection, complete pole frequency, 0 frequency, the DC gain and high frequency gain. And now we can determine now these values using the given values for this circuit. In that case, I will go first for the Bode plot to discuss that in more detail in general form, and then we will use the values shortly. And the Bode plot we have here on the vertical axis our gain, and on the horizontal axis our frequency. This is the gain in dBs, this is the frequency in radians per second, can be also of course in hertz. Here we have our 0 dB region, and this is now these are the values we have in this circuit as an example. So R1 is 950 ohms, R2 is 50 ohms, and we have 10 ohms for R3, and our inductor is 100 millihenry. So what happens? Well, if I calculate here the pole frequency using the values here, you get here for the ZD first, that's this part, is 57.5 ohms divided by 0.1, which is our inductor, and you get here 575 radians per second. The 0 frequency is determined actually again using this parameter, then Zn. That will be then 1150 over the 0.1 henries. That will give you 11.5 kiloradians per second. The gain for high frequencies can be determined using R2 and R1, which is then 50 over actually 1000, which is then effectively 1 over 20, which is then in dB is approximately minus 26.02 dB. So we have now the necessary information to draw our Bode plot using asymptotic lines. We also know that the DC gain is 0, so we actually start here at horizontal line 0, which is this red part, and then we approach our pole frequency, because that's the smallest part, and then the 0 frequency. And that's this, you see that actually here, so the pole frequency first, so 575 radians per second. Then it goes down with a slope of minus 20 dB per decade. Then we reach our 0 frequency, which is then our 11.5 kiloradians per second, and then we will actually level to 0 dB per decade. And this part is our minus 26.02 dB, which is our high frequency gain. So we start at 0 dB, and then we make a transition to this minus 26.02 dB, and we will also stay at that value. So the pole create actually this declining of this Bode plot, and then the 0 will again make it up. If you have another, for example, 0 will go up in the plus 20 dB per decade. Okay, now let's bring everything here. So this is the summary of the pole frequencies and the 0 frequency, etc. Now I will show you that in this simulations and then prove that this is indeed correct. So this is now the plot in the simulator. First I will also calculate the pole frequency in hertz, just divide this by 2 pi. Same for the 0 frequency, so you get here 91.5 hertz, and this is almost 1.83 kilohertz. And this is now the plot. You see here the frequency in hertz, that's actually what I did in order to compare that clearly. This is the gain and the vertical axis. And this is the circuit I have drawn in the SPI simulator. You see here the inductor and the resistor values. And we have here indeed that it is all correct. Why? Because look at the DC gain, which is 0 dB. The high frequency gain is minus 26.02 dB, as we have calculated. The pole frequency here, because I go here from 0 dB, I need to decrease by 3.01 dB, and that happens at 91.5 Hertz, which is exactly as we have calculated. This is the high frequency gain, so I have to go up, actually, so it is actually the opposite action by 3.01 dB, and that happens at 1.83 kilohertz. This is also the value which is 3.01 dB larger than the high frequency gain. So you see, everything is actually verified and according to calculation we have used using the extra element theorem. Alright, we have applied our extra element theorem on this circuit and determined our transfer function and verified that in the SPICE simulator. If you have any questions, please let me know and I will try to answer them as soon as possible. Don't forget to like and share these videos so that we can reach more people for these interesting topics. Thanks for your cooperation and see you next time in another video.